And welcome to the next class of Research and Academic Skills. And now I'm going to discuss chaos. Okay, so it kind of hopefully extends your perspective in understanding where science is at currently. And typically, science is far ahead of us in most ways. Maybe a good example is gravity. You might think that gravity is a force which has a fairly simple equation that relates to mass. But this is actually an obsolete theory, and more than 100 years ago now, physics experts have produced a better model of what gravity is, and it's an integral of space-time, radically more complex equation than what we study. Nevertheless, it is likely that in schools you also studied the false, so to speak, model of gravity because it's simple, because we can calculate with it, because it's functional. It serves the purpose. So in science, very likely every domain of science, the scientists are far ahead of where we are at. And in this sense, studying chaotic phenomena is really interesting because it shows how the paradigm, the way we think about life, research, all the things we encounter should have changed, right? There are certain facts that scientists came to realize which defy the traditional approaches, the way of thinking, which in this case is indeed the kind of strict causality. So we still think in terms of what would have happened, for example, if I did not prepare a lecture on chaos, but instead I prepared the lecture on management skills or something that I might find personally less interesting. The point is that there is no way of knowing what would have happened. Okay, we typically have a tendency to reduce the complexity of the situation and to think, oh well, if this would have been different, then something else would have happened. And this way of thinking makes sense only in a laboratory, only with the drastic reduction of variables, drastic simplification. So in our everyday life, these type of thoughts are essentially entertainment. They don't really make sense because there is no way of knowing what could have happened because the complexity of the systems, because of the amount of variables. Okay, so this kind of chaos theory is already showing us how the current paradigm is flawed. Nevertheless, it's gonna stick for a while longer. Okay, so first of all, I'm gonna just talk briefly about how we came to this. And maybe surprisingly, already in the 17th century, Newton has discovered that the three-body problem evades easy solutions. So if you have two bodies with gravitational attraction, the traditional gravity, you get elliptic motion. Okay, so there are some complexities here, but in any case, you can find a solution to this. If you have a third body with gravity, then we fail to produce a solution that will, as I said, maybe you remember, that will give us a shortcut to prediction. So the only way to find out the future is to get there. We cannot predict it using a shortcut. And this indeed is the case already with a simple equation that, well, simple more or less, but in any case, the equation that would describe the gravity and the motion of three bodies. Okay, so this three-body problem is your traditional kind of starting point here, and things developed very slowly initially. It took more than 200 years to explain in more detail what the three-body problem actually does. And the outcome was that Poincaré understood that we cannot solve it with closed-form analytical expressions. However, geometrically, we could. So essentially, we can create a model of this that we can run, but we cannot simplify it, and we cannot predict it. Okay, so actually that was the discovery of chaos, technically. What we have is a deterministic system, no probability, no randomness. Everything is very precisely spelled out, but we have aperiodic behavior. Okay, so we get a behavior where we have no repetitions, no settling state into a state. It all looks random, and it is very sensitive on initial conditions. So if any of the starting parameters change a little bit, then the system will evolve in a radically different way. Okay, so that's your aperiodic behavior, chaos, essentially, which is produced typically by simple equations in recursion. Okay, so that was another big milestone. However, it was not understood widely in terms of the implications. So it took quite a bit longer before we started to develop further along these lines. And then about 100 years ago, things started accelerating. There was an increasing evidence that such aperiodic behavior is not just a property of some weird feedback in mathematics, but that it's all over, that it's all around us. Okay, so nonlinear oscillators, one of the early domains where chaos was observed, vacuum tubes, radars, phase lock loops, lasers, all of these systems typically have a chaotic component which is observable rather than comes from a model like it did in Poincaré's work. Okay, and then from the 60s, we start to get real connection of the two domains. So because of the recursion in equations, typically you cannot run a chaotic system on paper. It just takes too much time to evolve it and to observe the properties. So we had the understanding that these recursive equations are weird, okay? We had the understanding that in the environment we have similar weirdness, but the two start to connect once we can actually run these equations and thereby observe and create the link between obvious appearances and the theories behind this. And then in the 70s, things really take off. So we have development of iterated maps, uh, logistic equation is probably worth studying as the simplest equation that will already give you chaos. We have the rise of the fractal theory. A lot of things in biology seem to be well approximated with this approach. Synchronization of crickets, flashing fireflies, many other things, non-linear oscillators found in biology. We have people looking at turbulence, also in relation to weather patterns, fluids, and so forth. And then we also get a kind of an overview of how this happens and the theory of the universal route to chaos. So suddenly all these separate systems and theories and models start to unite, and we start to observe these general properties of chaotic systems. So a lot of things happen in the 70s, and then in the 80s, things start to get the whole chaos theory, fractal images, they start to get really popular, and we get further experimental configuration. Okay, and then slowly we learn how to use this chaos to our benefit. Okay, so encryption strategies are actually based on entropy theory, very closely linked to chaos theory. And that's when we start to get the complex systems as a scientific field. Then network theory becomes more wholesome, graph theory, looking at the mathematics of things. And that's where we're at now. So all in all, a very exciting domain of study. For me personally, quite mind-blowing as you start to program code and essentially design systems that are fully defined, that are directly controlled, that are supposed to be failure safe. And as you do this, at one point, maybe for you this is just now, but you'll have to be convinced through practice, I propose. But hopefully now you will start to open this perspective and realize that defining things in detail actually gives us static systems that do not adapt and that will become obsolete very quickly. So if you think about IT tech, a computer from 20 years ago is near impossible to run. I mean, unless you're dealing with this, you archive them and you make sure that they continue to run. But what you see is that the systems that we build as fixed solutions become obsolete. Decades or centuries later, they're totally useless. Okay, so hopefully, likely, probably, inevitably, as a culture, as a civilization, we will build more and more adaptive systems that are supposed to and that will transform together with the environment. Okay, so chaos. I've explained some things about the term. There's very large amount of phenomena that belong to the class of chaotic phenomena. I've named just a few. So in theory, what we do here is examine recursive algorithms as a starting point. There's many other approaches. Obviously, you can just analyze the behavior and figure out whether there are chaotic properties to this. But for us, probably the more exciting thing, at least the starting point, should be just to understand how a very simple equation, a differential equation, will exhibit complex, unpredictable, chaotic, or random behavior. Okay, so a few more fields that we actually can describe using chaos theory. The issue being that this description will not give us prediction, okay, like we would expect from a scientific field. There is a paradigm which is still quite strong that the environment behaves according to rules and laws, and we are on the path of finding the ultimate rules and laws which will explain everything. However, this is by now just a layman's view, a kind of a poetic picture of the world, and scientists are way beyond this assumption. Okay, I've talked briefly about initial conditions, and I won't spend more time with this. Let us talk briefly about attractors as a very obvious property that we can view. So I've discussed orbits very briefly. So a chaotic system, the evolution of a chaotic system is what we call an orbit. Okay, so typically what you have, if I have a simple equation, okay, if I have an equation which is y is x squared minus a, okay, then if this is a simple equation, I will plot it with a parabola. I assume everyone understands this. Now, if I have the same equation, x squared minus a, but I don't run every possible input value and get every output from that input value and plot it, which is the procedure of creating a parabola, but instead I make it a recursive equation, I make a feedback loop. What I've done is that the x, the input value, will be the output of the previous calculation. So I don't take all the possible x values and calculate the y. I take a starting point, which is typically called a seed. I calculate the output from the equation, and the output becomes the next starting point. So actually from all the starting points, I will get an orbit, a sequence of points that succeed this seed. Funny. So what I get then is an orbit. Okay, so instead of having a graph which plots the equation, I create a feedback, so to speak, and I get an orbit. Okay, so what do these orbits do? So typically what you have is convergence towards a stable value, which is what we call a fixed attractor. So if you think about, for example, algorithm to calculate the square root of a number, it is a converging algorithm. It is a recursive approach. So the more I run the equation, the better I will approximate the result. So actually I have a convergence towards the value which is the square root. I won't go into the algorithm. I think it's called Newton's triangulation. But a similar thing holds for example, calculating the sign value of a number. Again, we have a recursive algorithm which converges to the result. And the more runs it has, the closer it will be to the actual result. Okay, so that's one potential type of attractor, a fixed attractor. The other type of attractor is essentially an oscillator. We get a periodic attractor. So we have an alternation between a certain number of values. So you could have a 2-point attractor. So you could have a recursive equation. You run it, you get positive number, next time you get a negative number, next time you get a positive number, next time you get a negative number. Okay, so if you have some algorithmic thinking developed, you can probably already think of an equation that will do this, that will oscillate between two values. Okay, and then finally, what we get, typically if we increase the growth factor in the equation, so these equations will typically have a growth factor and a limitation, such that if you cross the limitation, it kind of throws you back, but the growth factor throws you forward. So you essentially have two forces moving you up and down. And then if these forces are sufficiently strong, then we get a strange attractor or a chaotic attractor. We get an orbit where you cannot identify a single recurrent pattern. You see a pattern, which is your attractor, but actually the system does not go through the same point twice. So it is always giving you new values, new results. Okay, so even though we have a deterministic equation at the outset, we actually have an infinite detail, so to speak, in its outcome. And this is your typical basic textbook strange attractor called Hannon's attractor. So here you see the equation. So it's a two-dimensional map. We have an x and a y. And what you see in the equation is that the next x value, which is xn plus 1, so the index n plus 1 refers to the next value, can be calculated from the previous y value, which is yn, and the previous x value, which is xn. And similarly, the next y value, yn plus 1, in this case depends only on the previous x value. Okay, so in order to define such an equation, we need the two calculations, and we need the seed, we need the starting point, because you cannot calculate the next x unless you know the previous one. So we have a starting point where the first x is 1 and the first y is 1. So if you're interested, I invite you to code this. I mean, you might have already had some experience. I'm not aware of the whole structure of your studies. I would expect that similar things will be discussed or have been. But it's very mind-blowing, so to speak, that these two equations will yield such a complex shape. So on what you see there is the shape of the Hannon's attractor. If you run this equation and you plot the orbit, right? So at every calculation you plot the xy, you calculate, you plot the next xy, use that point to get to the next point. So you see from every point you get to the next point, you get this strange attractor. So what is strange about it is that we have a sense of a reliable shape, but actually this algorithm will never give you the same point back again. So all the points seem to go in a structured way, but there is no strict pattern. There is no repetition of a point. Every point that the algorithm yields will be a totally new point each time. Okay, so that's the mind-blowing thing. If you're interested in this, you can look up the logistic map, which is a one-dimensional map, so only single equation, and it already gives us chaotic behavior. such as this one, it is not as pretty, so to speak. So that's why I'm showing you this one. Okay, let's talk briefly about fractals then, which is kind of the popular side of things. It might be something that excites you as well. A lot of lovely graphics are produced in this way. So what we have as a crucial property of fractals is self-similarity. Okay, so what we have is that shapes seem to repeat. They don't repeat exactly, so they are not copied, but they are similar among each other. Okay. The interesting thing is that you don't only get similarity at the same scale, and you can think, for example, of a tree. So it's not just that branches are similar among each other. It is such that a smaller branch is structurally similar to a larger branch, is structurally similar to the whole tree. Okay, so at different scales, at different zoom levels, so to speak, you will get similar patterns. Okay, and I mentioned trees, but actually if you look at clouds, mountains, coastlines, we get these fractal shapes. And the point here is that it is useless to describe these by Euclidean geometry, by thinking of straight lines, squares and triangles and circles, because it is obviously something that has some type of regularity, but it's not Euclidean regularity. It's something that has to do with growth rather than design. Okay, so again, we're kind of seeing this distinction between conceiving a symptom, conceiving a final state, and conceiving an adaptive system, a system that will grow to develop a certain shape, which is not predetermined. Okay, now if you dig into these topics, one of the interesting things you might discover is that we define fractal dimension. So you understand that plane is two-dimensional, space is three-dimensional, line is one-dimensional. But actually we have things such as plane filling lines. So you can recursively define a line that will increasingly fill up the plane. And in its limit at infinity, it might completely fill up the plane, but it might only fractionally fill up the plane. And this is one way to approach the fractal dimension idea. It has to do with objects that are not fixed in an integer dimension, so to speak, like a line or a plane, but that are somewhere in between. Okay, so typically what you have then is that if we think about plane filling lines, okay, typically what you have is that the length of the line becomes questionable. Okay, because if it's a plane filling line, you imagine it has infinite length. However, in environment, we don't encounter infinity very easily. Nevertheless, we do see many fractal type objects. So typically, if you think of a coastline of an island, for example, and you ask the question, what is the length of this coastline? You will probably understand that it depends. What does it depend on? It depends on the zoom factor. Okay, so if I really zoom in and I try to follow the contour around every pebble, all the possible detail. I mean, there is an issue because the sea is moving, right? So it's not even fixed. But also, if I start zooming out, if I take a very low resolution picture, let's say, of the island, then the coastline will be shorter compared to a high resolution picture of the island. Okay, so that's the point, and actually the ratio of zoom and line length will also yield the number of the fractal dimension. Okay, so that's the crucial thing, and a similar thing called for other evidently fractal shapes like broccoli or similar things. Okay, and then we're just scratching the surface here. I'm kind of introducing concepts for you to go out there and explore yourselves. One of the interesting applications, which probably still has a lot of potential, is the frequency invariance of fractal shapes. Okay, so typically if we have Euclidean shapes, they have narrow band spectral properties, resonance, and such. Fractal shapes, because they have detail at various scales, they have a very broad band response. So we already have designs for fractal antennas to catch a broad spectrum of vibration. I'm not quite aware of a fractal speaker and a microphone yet, which could be very exciting because those are other domains where we desire broad bandwidth. So here are a few more. Typically, I'm going to now try to classify fractals. The basic class here is recursive function systems. So you could have a map, like you saw a Poincaré map, slightly different ones. What we frequently have is a geometric replacement rule. Okay, so typically all the things where you can reapply the same process to a geometrical structure, these are the situations where you will get different fractals. So we don't quite have enough time to look at all of these, but there is a list for you. These are all very fascinating, especially if you're into computer graphics. If you are, you probably know this already. But in any case, a lot of interesting recursive systems. Okay, now we can also create fractal shapes using escape time calculations. So in this case, we look at all the possible starting points, seeds. We still have a recursive function, but we don't look at the orbit, we look at the escape time of this orbit. So in a lot of situations, what will happen in a recursive equation is that it will escape to infinity. And then in escape time fractal plotting, what we look at is the amount of time it takes to escape to infinity. And typically this time is then signified with a color. Or indeed it could be just a binary thing, yes or no. If it escapes to infinity, we have a dot. If not, we don't. Okay, so in that sense, it kind of looks like a traditional equation because you take all the possible inputs. Okay, so we don't just look at one orbit, we look at orbits for all the possible inputs, and we don't plot the orbits, we just plot the escape time. There are a few terms there to look up, lovely graphics, please do. And I will show you a Mandelbrot set in a second. But just to finish the picture here, we also have a class of random fractals. So we can actually simulate fractal growth by having a not necessarily complex equation, but an equation that is designed to give us some randomness in repeating structure by using probability. Okay, so another few terms there for you to look up. And then to conclude, I will explain briefly how the Mandelbrot set is produced, which is the one that you see here, which is a self-similar shape. So what you see is that on the perimeter of these ellipses, you have a smaller version of the ellipses. And the point here is that it's an escape time plot, which means that every point was used as a starting point for the recursion, and then the escape time of that orbit is plotted. Okay, so what you have here is that all the points around the perimeter have escaped to infinity, and all the points inside have not escaped to infinity. And the interesting thing is that you can infinitely zoom into any of these shapes, because if you zoom in, well, then you just run the same algorithm in terms of all the possible points, looking at the escape time and just looking at the smaller window. And you can do this progressively, so you can look into the detail of this shape. And what you will get is this overall shape. And the stunning thing here is that the equation is this simple. So we have a complex number, z, and the equation says the next z is the square of the previous z plus a constant, right? So you see how it is not y equals x. It's not a standard equation that produces a graph. It is a recursive equation, one which specifies the next value based on the previous value. And if you run this equation for every point and plot the escape time, you get such beautiful forms. Okay, well, that's that. Thank you for your attention, and I will see you soon.